This is the Patapsco Wastewater Treatment Plant.
This is a nucleus.
This is a giant sequoia tree.
These are a bunch of numbers. Where am I? This is the remnant of a dead star. And this isn't 5 different videos. It's only when you put all these things together that you get something that you've probably already heard of.
But that's why I can't stop thinking about this. It is such a wild journey just to get one number with carbon dating.
Carbon dating.
Carbon dating.
Carbon dating. Seriously, where am I? Help!
Hi, Hank.
Hi, Tom.
Have you ever heard of carbon dating?
Yes.
Have you ever heard of something called carbon dating?
Yeah, Tom.
Okay, thank you for your time. After an extensive and thorough survey, it seems a lot of people have already heard of carbon dating.
It's that thing. No, that thing. The number.
Chances are, at least one of the numbers at your local museum comes from carbon dating, and the rest of them are still deeply influenced by it. Because, while carbon dating can't go back to the age of the dinosaurs, it's vital in helping us answer questions about our own human timescales. It's how we know the age of mammoth bones, ancient pharaohs, the Dead Sea Scrolls, even extinct human species like Neanderthals. So, what actually is carbon dating? Well, let me tell you. Merriam-Webster defines carbon dating as the determination of the age of old material by means of the content of carbon-14. But actually doing that is so comically easier said than done. And in my opinion, the actual process of doing the carbon dating and the story of how we figured out how to do it in the first place is just as interesting as any of the discoveries made using it.
Baltimore poop? Like the poop of Baltimoreans?
Uh-huh. Do you know how that gave us carbon dating?
No, I don't know about that.
All right, thank you. See? So how does this work then? Well, several articles from the journal Nature use this image when talking about carbon dating, which features a scientist using a, one of those, you know, that thing. We all know what that is. I don't need to say it. It's used in science. It's used in carbon dating. And it's called a scienceometer. But I actually don't blame them, because coming up with one image to represent all of the things that go on in carbon dating would be impossible. I mean, really, the only way to do it justice would be through, I don't know, like a 10-minute long YouTube video essay. Is that how long this is? I have no idea how long this video is going to be. Oh, wow. And that's because if we take a step back from our scienceometers, what we're trying to actually do here is bonkers. All of these objects, these artifacts and bones weren't stamped and dated ever. They've just been existing in the world. And now we're trying to retroactively turn back the clock on them. That's right, in this science video, we're taking on the ceaseless passage of time itself. Seems simple enough for my first YouTube video. Let me just take a quick peek into the literature, see if anyone's tried this before. Oh god! Oh, my hubris! Oh, wait. This one's actually pretty helpful. Archaeologist Janet Ambrose wrote an incredible review of the process of dating artifacts. And she starts by taking a step back from carbon dating and instead asks, how do we date anything at all? And so she starts by listing the requirements for a functional dating technique. First, we need something that changes in a consistent and measurable way. Second, we need to be able to measure a clean sample of that. Finally, we need a zeroing mechanism. Basically, we need to know when to start counting. Okay? And you're sure this will work? She's an expert. It is literally her job. Are you using Tinder on an iPad? All joking aside, I really love this rubric because of how abstract it is. Like, it feels like something you would come across in some sci-fi novel. And that's because what we're trying to do is really pretty sci-fi. Using so many different kinds of sciences, we're going to try to get an object to tell us how long it's existed for. Or to put it another way, what we're asking is, what in nature has been keeping track of time? And one answer you might be thinking of is trees.
This is illegal. Or rather, it would be illegal to cut down a giant sequoia tree like this today. Which is why I didn't do this. I know they're endangered. This was like this when I got here. At the American Museum of Natural History. This particular tree was cut down in 1891, but if we count the rings, we can figure out when it first started growing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18,
But it's not just a fun fact that trees grow rings every year. It's actually a whole field of study with an incredible name. Dendrochronology. Mwah! What a word! First thing to know about dendrochronology is we don't have to do this anymore. This is sometimes called a tree cookie, and as cute as that name is, it's not necessarily good for the tree. But these days, all you need to do is take a thin tube of wood that's the diameter of a pencil. As one researcher told Science, a woodpecker would do more damage. But the second thing I learned is that when it comes to these rings, the tree is only half the equation. Between the bark and the wood of a tree is a thin layer of cells called the cambium. And it's very hard to see because it's only a few cells thick. But it's this layer that slowly creates new wood, expanding the tree outwards. And do you know what affects growth? Seasons. So in the humid and warm seasons, these cells make a ton of wood. Then in the dry and cold seasons, the wood gets bunched up and forms the rings. So to be more accurate, what a ring shows us isn't a year, it's one trip around the sun and all of the seasons and weather that entails. Really, it's the Earth that's changing, the trees are just keeping track, and that's exactly what we're looking for. The only problem is that in the natural world, trees are basically the exception. Sure, things like rock and sediment can form these organized layers, but unlike trees, most organic matter is constantly moving and growing and shedding in inconsistent ways. As this dendrochronology textbook put it, trees with annual growth increments are a major exception to this. And still, even trees can't keep track of time after they're dead.
How long ago did you die? Sorry, I realize that's a sensitive question.
We're made of cells, not tiny hourglasses. So we're going to have to find a different approach. Okay! Radioactivity. Nuclear physics. Two words I don't want anywhere near me, let alone part of me, but too bad. They are! And that's because there's more to these words than all the dangerous things you're thinking of. I mean, those are still very real, but there's more. I'll be completely honest, it was only last year that I realized that nuclear physics is called that because it's physics involving the nucleus. Careful, that nuclear fallout is very dangerous. But it's our little nuclear friend here that's gonna help us turn back time. Is that showing up? Can you see that? It's really small. Hold on. Ooh, that was it. Hold on. There we go. This is the subatomic world. Any resemblances to Blender are purely coincidental. And this is a simplified model of a nucleus. But it's not just any nucleus, it's a carbon nucleus, which means it's in you and me and every living thing on Earth. And this bad boy, whew! This baby's rock solid. With all the forces that are at play at this tiny scale, this nucleus is super stable. But that's not the case for all of them. If you have an isotope of an element with too many or too few extra neutrons, throwing it off balance, or if your element is just too jam-packed with stuff, like with uranium, then then your nucleus will become unstable. And if that happens for long enough, eventually, something is gonna give. The atom will radiate something out and then decay to a more stable element. Or to put it another way, it will radiate out a particle, making it radioactive.
Hey, why would you do that here?
Sorry,
dangerous!
That was stupid. I always think of this as like the satisfying feeling of getting a rock out of your shoe finally. Like, I like to think it feels good for the nucleus. So this radiation and decay are two sides of the same coin. And while we can't predict when this will happen for any single atom, if you get a bunch of them together, you start to see a very regular pattern of decay. For uranium, it looks like this. And because of the curve of this line, we often talk about the rate of decay in half-lives. That is, how long it takes half a chunk of something to decay. And because we can measure the amount and rate of decay, radioactive elements work like hourglasses, which is exactly what we're looking for. But before we get ahead of ourselves, there are two big problems. The first is that not all these radioactive hourglasses are actually useful. Hydrogen-5, which is a hydrogen with 3 extra neutrons on it, has a half-life of 86 yoctoseconds. For perspective, traveling an inch at the speed of light would still take this many seconds. Meanwhile, one of the longest half-lives we've ever measured is for xenon-124, which has a half-life of this many seconds. And again, for context, this decimal place is the age of the universe. These are two of the most unfathomable timescales I've ever seen, and they both come from nucleuses. Fortunately, we've also found some elements that are a bit more practical. These are the half-lives of some commonly used isotopes in radiometric dating, which is the process of, like we've been saying, using these radioactive nucleuses as hourglasses. And I'll be completely honest, I spent way too much time making this one graph, so I'm just gonna keep it on screen for a little longer because I would hate if it just was there for a few frames and then disappeared, so yeah. Oh, the color corresponds to the atomic number of the element, which is cool. Can we play that animation one more time? Now, if you're just interested in doing something boring, like confirming the ages of dinosaur fossils or figuring out how old the Earth is, you can just pick one of these guys and be done with it. But if we want to answer all of our very human questions, we need something that decays at a human timescale. And some elements, like plutonium, happen to fit the bill pretty well. It's not too short that it would just fully decay in a few minutes, but it's also not too long that it would take billions and billions of years for any measurable change. But this is where we run into our second big issue, which is that, typically, ancient Mesopotamians weren't buried in plutonium coffins. But you can be, thanks to the sponsor of this video, Pluton. If you use the code TOMLUM at checkout, you can get 2 plutonium coffins for the price. Not only does our hourglass have to decay at a human timescale, it also has to be something that humans naturally have on them or in them. So, what if there was a radioactive version of the element that's already in every living thing? Carbon. And what if it just so happened to decay at a human timescale of a half-life of, I don't know, 5,730 years? Well, what if I told you that it's carbon-14. It's carbon with 2 extra neutrons. I wouldn't be making this video if this didn't exist. But to be crystal clear, this is incredible. There exists a perfect nuclear hourglass to help us turn back time. The only problem left then is, well, getting it. The first time we ever really studied carbon-14 was only in 1940, when it was synthesized with a cyclotron particle accelerator. And I know what you're thinking. Yes, it was that cyclotron that had a cameo in Oppenheimer and was, frankly, robbed of an Oscar. And to make carbon-14 with this thing, they were speeding up particles and smashing them into a sheet of graphite. Which, again, as far as we know, isn't something that ancient Mesopotamians were particularly known for doing all the time. So, what are we gonna do? We are so close! There exists this perfect isotope of carbon, and we even know how to make it! And we can't just sit around doing nothing, waiting for it to magically fall out of the sky. So what if we made a time machine that would let us... Oh! It literally falls out of the sky.
This is Earth, our little home in the solar system. You know, from the peaceful tranquility of outer space, all that hustle and bustle seems so insignificant. From way up, ooh, what's this? Oh, I didn't see this before. Oh, what? Hold no. Hold on. Pause. What? What was that? Those are cosmic rays. What? What? Where are they coming from? Oh, right. That's my job to explain. Hold on 1 second.
Hi. After we discovered radioactivity was a thing at the end of the 1800s, we of course started looking for it everywhere. This is a real quote from a Nobel Prize address. During the years that followed the discovery of radioactive rays, a search was made throughout nature for radioactive substances, in the crust of the earth, in the seas, and in the atmosphere. And when we went around looking, we found it everywhere. Like, everywhere. Like, how can it be everywhere? Is this thing working?
It was.
While a lot of this was coming from objects that were just naturally and not dangerously radioactive, like the potassium-40 in bananas, there was also just a slight radioactivity everywhere. And we now call this background radiation. There were some hunches that it was the Earth itself that was the problem, and so one scientist went to the top of the Eiffel Tower to see if there was less radiation up there. Say, do you think we could expense a trip to Paris for the next shot?
Right. So, first of all, I'm you, right? And second of all, we just had to edit in a picture of bananas a few shots ago.
So, no. And they found that all the way up here, there was less radiation. But other scientists wanted to go higher. The only issue being that the Wright brothers had only just successfully flown for the first time. Born too late to explore the Earth. Born too soon to explore the stars. Born at the perfect time for balloons. I am not kidding. Using balloons in science was, and still is, extremely useful. This is a picture of Victor Hess on a hot air balloon ride that would eventually lead him to sharing the Nobel Prize. So what Hess and others started to find is that as you go higher and higher up to around 5,000 meters, the amount of ambient radiation does decrease. However, if you send an unmanned balloon even higher to around 10,000 meters, then the radiation starts to increase again and can get up to 40 times the amount we experience on the ground. And that's because there was radiation coming from space. We now know that about 10% of the ambient radiation all around us comes from outer space via trillions and trillions of cosmic rays hitting our atmosphere every day. All right, now everyone say thank you to the atmosphere.
Thank you,
atmosphere.
Thank you for protecting us.
Now, the name cosmic rays absolutely slaps, but it's a bit of a vague misnomer because they're not really rays, they're actually tiny particles and loose nuclei. And we call them cosmic because they come from we don't know. So what do you mean we don't know where they come from?
So, again, I'm still just you.
Right, okay, yep, keep forgetting. To be clear, there are some cosmic rays we know about, like solar cosmic rays, which come from the sun. And it's because of these solar cosmic rays that we get the aurora borealis. At this time of year, at this time of day, in these parts of the world, localized entirely to the poles of the planet. But Hess once went up in a hot air balloon during a solar eclipse, wild, and still measured some radiation. And these rays we now know as galactic cosmic rays, which come from outside the solar system and possibly even outside the Milky Way galaxy. Scientists believe they come from things like supernovas and quasars erupting out of supermassive black holes, but some of them are somehow even more mysterious. In 2021, scientists measured the second strongest cosmic ray ever recorded. And when they looked up to the direction that it came from, they found nothing. As the researchers put it, possible explanations include a large deflection by the foreground magnetic field, an unidentified source in the local extragalactic neighborhood, or an incomplete knowledge of particle physics. But honestly, it makes sense that they wouldn't know where it came from. Remember, these aren't asteroids we're talking about. Most cosmic rays are just a single proton flying through the vastness of space. Alone. An untraceable, unremarkable speck in a boundless void. Until they hit our atmosphere. Now, any number of things could happen to our little friend. They could get swept away by the Earth's magnetic field. But they might smash into an atom in our atmosphere, causing a spray of loose particles. And one of those stray neutrons might hit an atom of nitrogen, bumping off a proton in the process and turning it into carbon-14. And that carbon-14 might fall down to Earth and land onto... Whoa! Did you just literally fall out of the sky? Where did you come from? I guess that doesn't really matter. This is amazing! Like, you are exactly what we're looking for. Oh! You are gonna help us learn so much about where we came from. This is not an exaggeration. Carbon-14 is what's known as cosmogenic, which means it mainly comes from, as this one paper so casually put it, cosmic ray bombardment. And as if this wasn't incredible enough already, the amount of carbon-14 produced every year is only around 7.5 kilograms, which is enough that we can measure, but also not so much that we're all dangerously radioactive. So for once, finally, ancient Mesopotamians would have had carbon-14. All living things have, completely unbeknownst to them. For as long as there has been nitrogen in our atmosphere, plants have been breathing in and animals have been eating tiny, cosmogenic, radioactive hourglasses. Which means all that's left for them to do is die. While we're alive, all of the carbon in our bodies is in a constant cycle of entering and exiting it through things like eating and breathing and shedding and pissing. It's really amazing the way we keep up this ship of Theseus of ours. And caught up in that cycle is that cosmogenic carbon-14, constantly being lost and then replenished again from the cosmic rays hitting our atmosphere. Which does mean we're constantly restocking our hourglasses with new ones before they've had any time to finish, which doesn't make them very useful. It's only when we die that this cycle, finally, stops. Then all the carbon in our bodies becomes the last carbon that will ever be in our bodies. It's all locked in, which means that carbon-14 is set. Death has to happen for carbon dating to happen, because while it might mean the end of our time, it's also when life's last hourglass can finally start. Now, you don't need to have an existential crisis in order to carbon date something, but sometimes it can be pretty helpful, because that last quote was actually from Willard Libby after he won the Nobel Prize for his help in creating the process of carbon dating. And to reach that part of our story, we need to take this theory one step further, because, after all, it's still just a theory.
A game theory.
And we need to find proof of it, and for that, we need a plan. Alright, here's the plan. Cosmic rays hit the atmosphere, making carbon-14. This then falls to Earth, where plants and animals eat it, and then they die.
Yeah, boss, I know. I've been watching the video.
Yeah, but most people are watching this on a half screen while they're doing something else.
It's a living.
And shout out to all the artists who are watching this while doing their art. Really, it's an honor to be able to give back. Anyway, before we start going nuts and trying to date real artifacts and bones or whatever, we gotta prove that this works first. And for that, we need a big sample of old carbon and new carbon. Because then we can clearly show that the old carbon decayed away its carbon-14 and the new carbon still has it. Boss, you're a genius! But where are we gonna get our hands on such a pure sample of old carbon and new carbon? I know just the place. This is Maryland. Any resemblance to Blender is purely coincidental.
Oh, no, I'm actually here. Couldn't fly out to Paris, but I could drive out here.
Baltimore, Maryland, home to Old Bay, the grave of Edgar Allan Poe, and the best state flag. But why are we here?
Well, one thing to keep in mind is that all the discoveries so far, the radiation, the cosmic rays, the carbon-14, have happened in the first half of the 1900s. So the first problem is they don't have a technology yet to measure a signal that weak, especially when the signal they're looking for is still theoretical. They need to measure something big to show this without a doubt. And the second problem was that the ambient radiation all around them was a much stronger and noisier signal that kept getting picked up instead. Now, the solution to that issue was actually more clever than you'd think. It's something known as an anti-coincidence counter. Rather than have just one Geiger counter measuring radiation, they put 11 all around the sample, because this way, any radiation coming from outside the chamber will have to pass through 2 detectors, whereas any signal coming from inside the chamber will only trigger 1, which lets us filter out the outside noise. It's beautiful how simple this solution is, and I know any game devs watching are thinking, nice. And as for our first problem, if we can concentrate our sample enough, then even these old tools will be able to pick it up. And the answer to that question is just as clever. Poop and farts. 2 words I don't want anywhere near me, let alone part of me, but too bad, they are. I'm not kidding! We all know that living things have carbon in them, but it's a bit more complicated than that because they're not just floating around, they're attached to things in compounds like this, and this, and this. But for what we're doing, we only care about the carbon, so anything that's not that is just getting in the way. So, one of the simplest organic compounds is this, carbon with 4 hydrogens. And this is methane. And it's really perfect for the job. It's a gas, which means we can compress and concentrate it, and it's pretty easy to get a hold of.
Now, getting our hands on some old methane is going to be a bit tricky because it's not like we've built up an industry that we've then become overly dependent on that relies on the finite resource of long dead organic material. So instead, I guess in this one specific instance, this is a good thing.
And as for the modern methane, well, some articles are a little bit cagey about where they got it from, which I find hilarious. As an article from the American Chemical Society put it, Libby reached out to Astrid von Gross of the Howdrey Process Corporation, who was able to provide a methane sample that had been enriched in carbon-14. Hey, where'd that methane come from, American Chemical Society? Huh? Fortunately, in their actual paper, in Libby and Anderson's landmark paper where they first demonstrate carbon dating, they make it crystal clear that they are using, quote, methane from
The Patapsco sewage plant of the city of Baltimore. Woo!
Now, since then, has the plant been mired in controversy? Yes. Sorry to milkshake duck a sewage plant.
But what you can never take away is the honor of the proud Baltimorean poops that helped prove carbon dating. In that monumental paper, they even say the exact day the sample was taken, September 2nd, 1946.
Ah, yes. September 2nd, 1946. The most important dump I ever took.
I am not kidding. The city of Baltimore gets name-dropped in Libby's Nobel lecture. But if you Google Baltimore carbon dating, you don't get anything. This city should be proud of its poops, because once this paper was published, carbon dating was off to the races.
That was not planned. Did the mic pick that up?
I don't think anything captures this period of excitement better than this graph, which I love because it so casually has an ancient Bible, artifacts from Pompeii, and several Egyptian pharaohs all on one graph. This is what Libby called the curve of knowns. And this was how Libby and his colleagues double-checked and calibrated their carbon dating numbers to known artifacts that we already knew the age of. Can you imagine calling up your friends and being like, hey, do you still have that ancient Bible? Well, you're not gonna believe this. Bring it to the lab. What's that? We can get a sample from several pharaohs? Let's go! I'm exaggerating, but they were really going wild with this. This quote in particular is hilarious to me. Libby used the radiocarbon dating technique to determine the ages of linen wrappings from the Dead Sea Scrolls, bread from the village of Pompeii buried by the eruption of Mount Vesuvius, charcoal from a campsite at Stonehenge, and corn cobs from a cave in New Mexico. He also used radiocarbon dating to determine that the last North American ice age ended about 10,000 years ago, not 25,000 years ago as had been believed. You know, corn cobs and shifting an ice age back 10,000 years. Stuff like this is why this is often called the radiocarbon revolution. There's this great story that Libby tells where he goes, quote, "The first shock Dr. Arnold and I had was when our advisors informed us that history extended back only to 5,000 years. We had thought initially that we would be able to get samples all along the curve back to 30,000 years, put the points in, and then our work would be finished. You read statements in the books that such and such a society or archaeological site is 20,000 years old. We learned rather abruptly that these numbers, these ancient ages, are not known accurately. And so, after they were done gathering all the known artifacts, quote, we had to go into the great wilderness of prehistory." And while carbon dating can't go back to the age of the dinosaurs, today it can go twice as far as Libby initially thought, up to around 60,000 years. And of course, there's carbon dating's greatest contribution to society. All of these absolutely buck-wild scientific diagrams that try to casually explain all of the bonkers stuff that's happening. This one starts with cosmic rays and ends with a dead cow. Multiple of them do! Now, obviously, carbon dating isn't without its flaws. Or, as this website put it, carbon dating accuracy called into question after major flaw discovery. Flaw discovery? If this is true, then many of our established historical timelines are thrown into question, potentially needing a rewrite of the history books. Oh man, this sounds pretty bad. Better actually read the rest of the article. In a paper published to the Proceedings of the National Academy of Sciences, the team led by archaeologist Stuart Manning identified variations in the carbon-14 cycle at certain periods of time, throwing off timelines by as much as 20 years! Ah! Now, to be fair, dates do shift around in carbon dating by hundreds or thousands of years, as this article from 2020 notes in less clickbaity words. But after seeing all of the wild sciences that go into this, of course it does! We're not just pointing a scienceometer at some bones. Every single step of this process can and has been improved by leagues since Libby's time. Scientists have even figured out what this thing is. Finally, gosh! Okay, what is it? It's an electric rasp. It's basically just a glorified Dremel for shaving off bits of carbon to analyze. Which I knew! That was the joke! Really, this image is the first step in our modern carbon dating process. It's a Dremel. It's just a Dremel. There's an amazing video from GNS Science that walks through their whole process of dating a single sample. And it features so many casually wild moments of them preparing the sample. Science rules! And then, to separate out the carbon-14 from the sample, they blast it through a particle accelerator. But in my opinion, the biggest advancement in carbon dating is shown right here. And this isn't even all of it. There's this whole other... Let me show you. I'm proud to present to you tonight, in all its unedited glory, my favorite part of carbon dating. It's gonna take a bit because there's a lot of numbers. I'm starting to see now why they chose not to show all of this. Let me just explain it. Yeah. Remember this graph, the curve of knowns? Well, it wasn't just Libby and his colleagues that were excited to add to this. Scientists were finding all kinds of ways to make this calibration curve more accurate, including things like taking into account the rise of carbon dioxide from the Industrial Revolution. And finally, in 1998, the first international calibration curve was published, aptly named IntCal. And that is exactly what these numbers are. Basically just a more advanced version of that original curve of knowns. Except this time, with the help of scientists from across different fields, across different times, and across the world. And IntCal has been updated as recently as 2020 with data from things like plant macrofossils and stalagmites from underwater caves in the Bahamas, among so many other things. Look how many authors there are! Look how many! These are all the regions of our entire planet that are covered by IntCal 20, which is a lot, but there's still a lot of exciting science to be done. When I first started writing this, I wanted to end by saying something like, now, carbon dating is accurate to within plus or minus this many years. But I now realize that asking the question, how much has carbon dating improved, is sort of like asking the question, how much has food improved? It's like, overall, yes, clearly it has improved, but the specifics depend on where and when you're talking about. There is a separate IntCal dataset for objects from the northern hemisphere and objects from the southern hemisphere, and a separate one for marine objects, because of course, that makes perfect sense. And, much like food, the one thing that has universally improved carbon dating is collaboration. And do you want to know who the most important contributor to this data is? In a paper announcing the new versions of IntCal in 2020, the very first line reads, "The main backbone of radiocarbon calibration has been and will continue to be tree rings dated by Dendrochronology." This was foreshadowing!
This was foreshadowing!
You can compare the number you get from counting the rings to the number you get from carbon dating the rings. In fact, the first standardized calibration curves from the 1960s were made using tree rings, and trees are still helping us with this today. And when I read that line about how important dendrochronology is to carbon dating, that's when I knew I wanted to make this video. Because for me, that's what's so amazing about all this. The fact that you need nuclear physicists and chemists and historians and biologists and astronomers and geologists and archaeologists and anthropologists and mathematicians and computer scientists and dendrochronologists all working together to make this happen. While only Libby's name would go on the actual prize itself, for his Nobel lecture, he wrote, "The large number of people who have contributed to the development of the radiocarbon dating technique are largely responsible for whatever success it has had. Of all the rewards of research, none is greater than the meeting of people in different fields and the finding of interests in common." And what greater common interest is there than trying to take on the passage of time itself, to try to learn more about where we came from? On their own, each of the things we've learned about has been amazing. Okay, well, some of it was literally poop, but most of it was amazing. But it's only when you put all these things together that you get something incredible. Sort of like a metaphor for people working together. Or like the scientists that all work together to make it. That was the intention. That's why I wrote that. The video's done, by the way. Thank you for watching. Don't forget to like, comment, and subscribe. Hi, it's me, Tom Lum, from the video you just watched. I hope you liked it. It's my first time making something like this, and if you did like it, you might also like a postcard to remember the video by, signed by me, Tom Lum, from the video you just watched. It's been a long video, my writing brain is done. But you can only get these if you sign up in the next 30 days for my new Patreon that I'm launching today. I'll be sending out a signed postcard of your choice to every single patron at every single tier. And for the higher tiers, I'll add a personal message or a doodle of dubious quality. For this video, I learned Blender, got a green screen, dusted off my D3 knowledge, drove to Baltimore, got to work with the American Museum of Natural History, and did all the music and editing. It's just me here, and I loved doing it. I love being independent like this. But I made a joke earlier about not knowing how long the video is gonna be, but I genuinely don't know what the view count will look like down there. I have no idea how well this is gonna do. The algorithms are fickle. So I can't promise you a consistent schedule yet, or even a consistent format, but I can promise you, whatever I do here, it will be something that I'm genuinely excited about, and hopefully something that will make you laugh and learn. And if you would like to help me make the jump to make more of this, I would love your help. Over on the Patreon, I'd be happy to do a project breakdown of this video, talk about the tech and techniques, do a bookshelf tour to talk about all the stuff that's always behind me, or maybe a podcast where I chat with other creators. Whatever it is, we'll figure out what you want to see over on the Patreon. Patreon.com/TomLum. With me, Tom Lum, from the video you just... And this is the part of the video where patron names like yours would show up and I would thank them. But it just launched, so who are these people? Well, a bit ago I made a silly video about how I got laid off, and a few people tipped me in the comments just because, so I wanted to especially thank these pre-patrons for believing in me. Thank you. So, thank you again for watching. I hope to see you on the Patreon, but until the next thing, I'll see you. This has been Tom Lum from the video you just watched.